So, how do you find the hidden weak points inside a material? The one spot that could cause a catastrophic failure. Well, today we're going to crack that very case. Think of it as a mathematical detective story, and our main clue is one of the most elegant graphical tools ever created in engineering.
All right, here's our game plan. First, we'll set the scene with something called plane stress. Then, we'll dig into the central mystery. What happens when you look at stress from a new angle? After that, we'll follow the mathematical clues to derive the equations, which leads us to our big aha moment, Moore's circle. And of course, I'll show you exactly how to draw the thing and why it's basically an engineer's secret weapon. Okay, so every good detective story needs a crime scene, right? So let's establish ours. We're stepping into the world of two-dimensional stress, or what engineers call plane stress. So what is plane stress? Well, it's this really clever simplification. It lets us take a complicated 3D object, say a thin sheet of metal, and just analyze it in 2D. The whole idea, the key assumption here, is that if something is super thin, stress just doesn't really have room to build up in that thin direction. So we can kind of just ignore it. It makes life a whole lot easier.
Yeah, look at this. For a thin sheet like this one, it's just really tough to build up any meaningful stress perpendicular to the surface. It just can't support it. So by assuming those forces are basically zero, we get to take this big, scary 3x3 stress matrix and shrink it down to a much friendlier 2D state. And trust me, that makes the math so much easier to deal with. Okay, the scene's set. Now for the central mystery. Here's the kicker. The stress you measure on a material, it's not some fixed absolute number. Nope, it's all about perspective. It completely changes depending on the angle you're looking from. And this right here is the million-dollar question for any engineer. I mean, think about it. A beam or a metal plate might look totally fine from our normal, XY point of view. But what if we just rotate our view? We might suddenly uncover a hidden angle, a hidden plane, where the stress is dangerously high. Our entire job is to find that exact worst-case scenario.
So look here. On the left, you've got your standard stresses, the normal stress, sigma, and the shear stress, tau. We know those. But if we just rotate our viewpoint by some angle, we'll call it theta, boom, those values transform into a totally new set of stresses. The whole game is to find that one specific angle, that one theta, that reveals the hidden absolute maximum stress.
All right, let's get into it. To crack this thing, we've got to follow the mathematical breadcrumbs. In our investigation, it starts with the absolute basics, with first principles. So clue number 1 comes straight out of Physics 101. Just imagine we take our little square of material and slice it into a wedge like this. Now, we know that for this little piece to just sit there, to be in equilibrium and not go flying off into space, all the forces acting on it have to perfectly balance out. The sum of the forces in any direction has to equal 0, simple as that. And when you do all that force balancing, you end up here. This is our first major break in the case, the stress transformation equations. Now, don't freak out, you don't need to memorize these things. The point is, they work. You can plug in any angle you want and get the new stresses. But they're kind of clunky, right? They're messy, and they're hiding a much more beautiful pattern just underneath. And here's the breakthrough. This is where we clean up that mathematical mess. We use this nifty little trick from trigonometry, these things called double angle identities, and just look at the result on the right. See how much cleaner that is? This new, elegant form, this is where the hidden pattern we've been searching for finally starts to show itself. And while we're doing this, we stumble upon something really profound. We discover these things called stress invariants. What are they? They're specific combinations of stress, like, for example, the average of the normal stresses that never change. No matter how you rotate the element, this value stays constant. It's like the fundamental fingerprint of the stress state, a piece of evidence that can't be altered.
So, okay, where are these simplified equations actually leading us? Well, get ready. This is the moment in our investigation where all the clues snap together and the whole case gets blown wide open. If you just stare at those cleaned up equations for a minute, they start to look familiar, don't they? I want you to think way back, maybe to high school geometry. Does that form ring a bell? They're the parametric equations of a circle. And we have one absolute genius to thank for this incredible insight. Back in 1882, a German engineer named Christian Otto Mohr had this amazing realization. He saw that this whole complex stress problem didn't need pages of tedious calculations. It could be solved
with a simple drawing. And here it is, the big reveal. All of those complicated equations, they map perfectly onto the geometry of a circle. All we have to do is set up our axes. So normal stress, that's sigma, that's our horizontal axis. And shear stress, tau, that's our vertical axis. The amazing part is that the center of the circle and its radius are defined directly by the stresses we started with. And get this, every single point on the edge of the circle represents the exact state of stress at a specific angle inside our material. Mind-blowing, right?
Okay, so we found this incredible tool. Now let's actually learn how to use it. We're going to build our very own Moore's circle step by step.
It's just 6 simple steps. Don't worry, it might look like a lot, but it's a super logical process that basically just turns a bunch of numbers into a picture.
All right, let's do the setup first. Steps 1 through 3. First up, you just identify the stresses on the vertical face, we'll call that point V, and the horizontal face, point H. Next, we use those stresses to create 2 coordinate points. Now here's a key detail you have to remember, the sign convention. For Moore's circle, a shear stress that would cause a clockwise rotation is considered positive. Weird, I know, but that's the rule. Then we just draw our axes, normal stress on the horizontal, shear stress on the vertical. Okay, time to execute the final steps. We plot our 2 points, V and H, on the graph. Then we draw a straight line connecting them. Right where that line crosses the horizontal axis, that's the center of our circle. Now you just grab your compass and draw the circle. And here is the single most important rule you have to remember. A rotation of theta in the real world on our actual material corresponds to a rotation of 2 theta on Moore's circle. Always double the angle. So what's the big deal here? What's the bottom line? We've basically taken a whole page of messy trigonometry and replaced it with one single super intuitive drawing.
I'm not kidding. This thing is the ultimate engineer's cheat sheet. You see those 2 points where the circle crosses the main horizontal axis? Bam! Those are your maximum and minimum normal stresses. We call those the principal stresses. And the very highest and lowest points of the circle? That's your absolute maximum shear stress. Every answer we were looking for, the solution to our whole mystery, is right there in one elegant picture.
So Moore's circle literally gives us a way to see the invisible forces swirling around inside of materials. It's an amazing tool. So now that you get it, now that you can visualize stress, think about it next time you cross a bridge or walk into a skyscraper. What are the hidden forces holding our world together? And how might you see them just a little bit differently now?